Hey everyone, welcome back to another DIYson Build Log. This is the first video I ever recorded of the DIYson project, and it was taken almost exactly 3 years ago. At that time, I wasn't planning on doing these build logs or sharing the project in any way, but I was just so overjoyed and kind of amazed that I managed to write code that controlled this high power LED that I felt compelled to just record it. Since that day, I've been very slowly learning more and more about the basic electronics concepts needed to make the DIYson work. From adding simple input buttons to designing my first PCB and even some additional weird ones. These days, I'm at a point where I can look at version 1 of the DIYson control board with just enough awareness that I see little opportunities for improvement start to crop up. It's been slow going and incremental, but pretty satisfying and a little addictive, but I try not to get too carried away. Recently, I changed almost every component on the DIYson control board and added a bunch of new ones. Version 1 of the control board was quite simple, but a custom PCB was essential for stuffing all of the required components and their wiring into the limited space of the electronics housing. Compactness is one of the driving constraints of this project, and in keeping with that theme, we only have about 1.5 cubic inches of space for key components like the microcontroller, its 5-volt buck converter, and the LED driver module. And these three are pretty happy working together here, so why change them? Let's start with the LED driver. I replaced the original one because it gave off a high-pitched whine and made the LED visibly flicker. The new driver uses an analog reference pin instead of the traditional PWM, so it's completely silent and flicker-free. Nothing has changed here since the last build log, so check that out if you want more detail on this. I've also mentioned recently that the microcontroller is due for an upgrade. While the QT Py SAMD21 is a perfect fit for the DIYson in just about every other way, it has very minimal storage, and I ended up running out of space while I still had a bunch of software features left to add. Luckily, there's a drop-in upgrade available in the QT Py ESP32S2, which increases the storage from 256K to 4 megabytes and the RAM from 32K to 2 megabytes. So that's a 16 and a 62x upgrade. Importantly, it also has all the other essential features the DIYson needs, like native USB support, CircuitPython, support for capacitive buttons, and an onboard DAC for controlling the driver. Turns out there's only one board from Adafruit in this form factor that does all this, and luckily, I found it. Powering the QT Py, we have this 5-volt buck converter breakout, also from Adafruit. Being a breakout board, it has some space inefficiencies like this little mounting hole and the large headers. Beyond that, it's only rated for 21 volts, even though I've been setting it 24. This replacement has the same footprint, handles up to 36 volts, and is even made by Recom, the same manufacturer as the LED driver, so I think there's some kind of like synergy bonus I get with that. With the original core components upgraded, I felt like I had the lamp fundamentals working well, but beyond that, I want to do some clever stuff like automatic brightness and temperature monitoring, and for that, we need some sensors. You've seen me tinker with some basic analog sensors so far, but in the spirit of getting carried away, I can't help but wonder if we can do better. The ambient light sensor, like the old buck converter, is in a breakout board form factor, which is just not an efficient use of space on a PCB that's about to get pretty crowded. The current light sensor module takes up a lot of space for just two tiny components, the light sensor plus a capacitor. What I loved about these pre-packaged breakout boards is that they come with thoughtful documentation by Adafruit, which includes a bunch of implementation examples, but as I'm leveling up my electronics skills, I couldn't help but wonder how much further we could go if we graduated from this pre-packaged format to a standalone sensor. So when we talk about measuring ambient brightness on the DIYson, what we actually care about is how bright a space feels to our human eyes. Analog sensors like this don't really see light in that way. They just output a raw voltage coming from a phototransistor, which doesn't necessarily match how humans perceive brightness. So until now, I've had to take that output from the analog sensor and do some scaling and manual calibration in the software to convert it into a lux value, which is just a way of measuring light that's weighted towards human perception. But some sensors will actually do this work for us. They come pre-calibrated and report lux directly, saving a bunch of time and guesswork. The VEML 7700 not only looks exactly how I imagined a light sensor would look, but it's a high-resolution digital upgrade that does exactly what we want, accurately reporting a meaningful brightness measurement. The shorter and slimmer form factor also has a practical benefit because it's one of the few components that I'm mounting on the back of the PCB. My plan here is to mount this on the top and have a little cutout in the enclosure so light can get to the sensor. I'll also put a little window here to make it flush with the surface. But more on that later. The light sensor isn't the only component going digital. The old temperature sensor is getting upgraded to a 12-bit digital alternative, which increases accuracy from plus or minus 3 degrees to just 1 degree Celsius. I'm also moving from this through-hole style to a smaller but still hand-solderable surface-mounted chip. A tip for fellow electronics beginners out there, when browsing through hundreds of components online, it's not always intuitive which one is going to hit that sweet spot where it's small enough to fit in your project, but it's still large enough for easy hand soldering. And more than once, I've chosen parts based on their photos and descriptions, only to find that when it arrives, it's not the size I expected. By now, I am starting to get the hang of these footprint specifications, but early on, I wish I had referred to one of these PCB rulers, which shows the physical footprint and pad size for common components. For the DIYson, I found that this SOIC form factor is ideal for chips and sensors, and for diodes and resistors, I tend to intentionally size up to one of these larger footprints, which are way easier to solder without a hot plate. And when it comes to the temperature sensor, there are smaller options out there, but this one strikes that perfect balance between compactness and ease of assembly. Another cool thing about the light and temperature sensor is that they can both use the I2C interface to talk to the QT, meaning each device has a unique address, and I can use the same two pins to communicate with both of them and any additional I2C devices I might add later on. All right, so with all the new components and code changes, this setup's actually been working great on the breadboard, except for one thing. Back around the time of that first video, I noticed that when you first power up the lamp, the LED momentarily flashes at full brightness, even though the lamp is off. Back then, I really didn't know enough to understand why this was happening, and I kind of thought, well, if I ever get far enough in this project that I'm able to address this tiny, mundane problem, I'll be in a really good place. And well, here we are. When the system powers up, both the QT and the LED driver get powered up at the same time. The LED driver's brightness is controlled by an analog reference pin, and that pin expects a voltage between 0 and 5 volts. At 0 volts, the LED is at full brightness, and anything above 3.3 volts will turn it off. You might already see where this is going. The QT takes a second or two to boot up at first, so during that time, it isn't sending any signal at all to the LED driver. So during that time, that reference pin floats at or near 0 volts, and the driver, doing exactly what it's supposed to do, turns the LED on full blast. Then, once the QT boots, our code sets the control pin to 3 volts, and the LED turns on as it should. It's not a huge deal. It only happens when you first plug the lamp in, but stubbornness prevails and I'm fixing it. If you think about how you'd solve this mechanically, which is how my brain tends to work, what you'd want is some kind of tiny robot that plugs 5 volts into the LED driver's control pin during boot, keeping the LED off, and then unplugs it once the QT is booted, allowing the QT to take over. It turns out the electronics equivalent of this hypothetical robot is called a load switch. It's a tiny chip which I can only assume has a clever robot inside that allows a signal to pass through until something tells it to stop. So in our case, a 5-volt signal will pass through to the driver control pin until the QT boots up and tells the switch to stop. That 5-volt signal keeps the LED off during boot, but lets the QT fully take over brightness control responsibilities once it's ready. Now the lamp honors its off state until someone presses the power button. For the record, I did try a couple of simpler solutions here, like a pull-up resistor, a MOSFET, and a transistor, but the little load switch is what ended up working, and it's been flawless. One of my favorite things about working on the DIYson is programming different features into the lamp and testing them out in real time. And I really want to allow folks who make their own DIYson to reprogram their lamp whenever they want because it's really fun. The problem is that the QT really hates being plugged into 2 power sources at once, and I've killed a few of them this way. My workaround has been just to unplug the 5-volt input whenever a USB cable is plugged in, but once this all gets finalized into a new PCB, that's not really an option. So I'm adding a little power control circuit just for this use case. It uses another load switch and a MOSFET to make sure that the QT is only ever powered by a single source. This lets us reprogram the QT anytime without worrying about backfeeding or frying the board or even rebooting for that matter. This is one of those edge case things that I'm planning for, but I bet there's at least 1 or 2 people out there who will appreciate this. And for those people, I've made this variant of the electronics housing with a little USB-C size cutout just for you. With these upgrades, the brains of the lamp just got a bit smarter, but there's still a few mechanical puzzles to solve. First, I need to make a few changes to the electronics housing for the new control board. Mainly, that boils down to making room for the ambient light sensor, which I really want to place centered between the end of the buttons and the edge of the enclosure. So to do that, I'm extending the PCB by about 15 millimeters and placing the light sensor right around the very edge of it. I made this cute window for the light to come in through, and it slots up under the PCB and sits flush with the top surface. I didn't have any clear filament lying around, so I ended up doing this on a resin printer. I need to sand and polish this a bit more, but I'm really liking the way that it turned out, and I can't wait to see the light sensor underneath it. Right next to where the light sensor will be is a new PCB mounting hole. My first strategy for mounting the PCB was pretty bad. Due to the space constraints in the housing, I had to use these really small screws which were just not up to the task of reliably grabbing onto the PLA and holding the PCB in place. The 3 millimeters of material underneath the control board is just a bit too thin to fit a threaded insert that would fix this problem, but down here after the PCB ends, suddenly there's 5 millimeters of material to work with, plenty of space for a carefully installed threaded insert. What has become one of my favorite uses of 3D printing is printing off random samples of parts before they get manufactured. So I'm using this 3D printed stand-in for the new control board PCB to dial in the perfect fit. On the opposite side of the enclosure, I added this lip, which together with this retaining clip holds everything in place, kind of like an M.2 drive if you've ever installed one of those. Then when the enclosure is mounted on the arm, this little clip is small enough to rest inside of the rail channel. The reason this clip looks a little funny is because it helps me solve another problem. I need to connect the control board to the super track. There are a lot of easy ways we could do this, but we have to keep in mind that I'm dumb, and because of that, there just can't be any visible cables here. I knew going into this problem that I needed to find a cable assembly whose connectors fit within the roughly 6mm rail channels. I tried a lot of these and I managed to find the solution in the Molex Microlock Plus series, which is one, really nice looking, and two, comes in a bunch of really useful different pre-assembled lengths. If I center a mating terminal on the control board and add another to the end of the super track, they will both fit comfortably within their respective rail channels. And from there, I just need to find a way to route the cable through the housing wall while keeping it totally hidden. The PCB kind of gets in the way here, so I use the PCB clip to guide the cable away from the PCB where I can then submerge it into the enclosure. From there, I route it into the wall, around the screw, and out the back of the enclosure, and from there, I can plug it into the super track. I've added this little cave here for the excess cable so I can slide the super track right into the housing and it hides the cable completely. Seeing as this was working really well, I decided to make things a lot harder. I think what happened is I saw a Nintendo cartridge and I thought, man, wouldn't it be cool if the Super Track just slotted itself into the housing like a game cartridge slots into a console? Yeah, so there are a couple of issues with this that make it harder than it sounds, which I won't go into now, but even just imagining the little header sticking out from the enclosure and that moment during assembly where you get to slide the Super Track into the enclosure is just so exciting to me for some reason. I really wanted to do this and it was kind of eating away at me. And this is where project goals really come in handy for me, because when you evaluate this cartridge solution versus the cable solution against the project goals, the cable solution that I've already implemented is just too good. It's off-the-shelf components with no modification. It's pretty foolproof for repeated assembly, and that connection is going to be super reliable. I'm sure there are decisions I've made on the lamp that from the outside cause people to wonder, why would you do it that way? There are more clever or elegant ways to solve that problem. And sometimes that is just my own limitation and my own limited cleverness. But also I think there are times like this where the less clever solution aligns best with the project goals like reliability, cost, and ease of assembly. So I wanted to share my thought process here. So with these changes to the enclosure looking pretty good, I'm just about ready to order the new control board PCB, and I've added a couple things. So there's a couple of necessary pull-up resistors on here for the new components, and I've also added a couple of capacitors for power reliability too. For the load switch, I switched it out for this miniaturized one rather than the through-hole mounted one that I was using to test on the breadboard. I'm really excited to order this new PCB and test out all the new components working in the DIYson, but before I do that, I need to make some changes to the super tracks, and I want to order all the new PCBs together at the same time. So in the next build log, I'll share those super track updates with you. Obviously, I'll share the new PCB for the control board with all the components on it. There's also a couple of changes I need to make to the carriage, and some big changes I need to make to the base. So all that will be coming in the next build log. And if everything goes well, that might just be the final build log for the DIYson. As I'm wrapping up the DIYson, I'm thinking about what the next project could be, and I need to ask for your help so that I can keep making projects like this and continue to share them with you in the form of these build logs. And I think the best way to do that would be through Patreon. So the obvious thing that Patreon helps with is project costs and camera equipment, but the main reason that I wanted to do this is because I want to share more regular and frequent updates with people who support me. So for the Patreon, I thought it'd be cool if for every patron, we would do regular live streams and hangouts where I can share what I'm working on, ask about what you're working on, and chat and answer questions and just hang out. So every member will get access to that. And if you choose to support me at like a higher tier, there's some other perks, including I'll send you some stickers if you want them. So if for whatever reason you want to watch me descend into obsession and madness about a project that isn't the DIYson, and I have a lot in mind, you can do that by supporting me on Patreon. And it would really mean a lot to me just to know that there's people out there who want to see more projects like this. All right, that is going to do it for this build log. Thank you so much for watching. Thanks for sticking with me on this project because I know it's been a long one. And hopefully in the next build log, we can wrap things up, and I will see you there. See ya.